Since the publication of the science paper in 2021 by Shimizu and co-workers from the University of Calgary, CALF-20 is generally regarded as a leading candidate for use in pressure swing adsorption technology for CO2 capture from humid flue gases. This science paper reports experimental data on the influence of moisture on the loadings of CO2, and from breakthrough experiments, the experimental data on the component loadings of CO2 indicated by the red circles and water indicated by the blue triangles have been presented in the science paper as a function of the percentage relative humidity. If we compare the experimental data that are determined from breakthrough experiments for the component loadings with from experiments with those estimated from the ideal adsorbed solution theory, we note that there are significant deviations from the IAST estimates. For values of relative humidities lower than about 45%, the adsorb phase is poorer in water and richer in CO2 than anticipated by the IAST. This is due to segregated nature of adsorption, wherein the CO2 molecules and the water molecules are not located at the same adsorption sites within the channels of CALF-20. CALF stands for Calgary Framework. Furthermore, we note that for percentage relative humidities higher than 45%, there are significant deviations of the component loadings from the IAST estimates, but in this case, the adsorb phase is richer in water and poorer in CO2 than the values anticipated by the IAST. This is ascribable to strong hydrogen bonding between water molecules, and CO2 faces increased competition by the water clusters that are present in the framework. These explanations are provided in my papers that are listed here, both in separation and purification technology. I have prepared several videos on this topic. See parts 1 to 8, videos titled Thermodynamic Non-Idealities in CO2 Capture. Today I address a different aspect of thermodynamic non-idealities. Firstly, rather than rely on experimental data from breakthrough experiments that are by very nature not precisely isothermal, we examine experimental data published recently in which true mixture adsorption equilibrium is determined in a technique that is called a thin film approach. Using this approach, the experiments were conducted under 3 different temperatures to examine the influence of increased temperature on deviations from the IAST. So let's first examine the experimental setup to determine adsorption equilibrium for CO2 water mixtures with varying percentage relative humidity. Researchers from Matrix Sensors Incorporated in San Diego, California, have developed a novel technique that measures mixture adsorption equilibrium using thin films of sorbents deposited onto sensitive micro-electromechanical system transducers, MEMS. This technique is fast, requires very little material, and enables real-time monitoring of binary gas mixture adsorption in MOFs and other nanoporous materials. This development is reported in this paper titled Thin Film Approach to Rapid Quantitative Measurements of Mixed Gas Adsorption Equilibrium in Nanoporous Materials. And this paper is co-authored by researchers from Matrix Sensors and also researchers from the universities of Amsterdam and Calgary. The thin film approach was used to measure CO2 water mixture adsorption equilibrium in pristine CALF-20 materials. The experimental data on the component loadings for CO2 indicated by red circles and water, blue triangles, for adsorption of CO2 water mixtures at a temperature 298 Kelvin are shown in this graph here as a function of percentage relative humidity. The total pressure of CO2 and water is 15 kilopascals. We note that the experimental data also shows strong deviations from the estimates of the ideal adsorbed solution theory. The continuous solid lines are the real adsorbed solution theory fits of the experimental data. Another way to demonstrate the deviations of the experimental data from the IAST is to plot the mole fraction of CO2 in the adsorbed phase on the y-axis as a function of percentage relative humidity. For values of percentage relative humidity is lower than about 30%, the adsorbed phase is richer in CO2, i.e. poorer in water than anticipated by the IAST. On the other hand, for relative humidities in excess of 30%, the adsorbed phase is significantly poorer in CO2, i.e. richer in water than anticipated by the IAST. The RAST modeling using the Margulis model for activity coefficients is shown here by the continuous solid lines. These are the activity coefficients for CO2 indicated in red and for water in blue. This is the plot of the excess Gibbs free energy as a function of mole fraction of CO2 in the adsorbed phase. The experimental data, as reported by matrix sensors, is thermodynamically consistent. Further details are provided in the preprint I had referred to earlier. Using the thin film approach, the mixture adsorption equilibrium was also determined at higher temperatures of 308 Kelvin and 318 Kelvin. The experimental data for water loadings indicated by the blue triangles and the CO2 loadings indicated by the red circles are compared with the estimates of the IAST. And we note that with increased temperature, the deviations of the experimental data from the IAST estimates is progressively reduced. In other words, thermodynamic non-ideality effects are of decreasing importance with increased temperature. A different way to demonstrate the influence of temperature on deviations from the IAST is to plot the excess Gibbs-free energy divided by RT to make this dimensionless as a function of mole fraction of CO2 in the adsorbed phase mixture. The experimental data are indicated by the red circles at temperatures of 298 Kelvin, 308 Kelvin, and 318 Kelvin. We note that the values of the excess Gibbs-free energy show a gradual reduction with increased temperature. The excess Gibbs-free energy quantifies the deviations from ideality. So the important takeaway message from our presentation today is that thermodynamic non-idealities generally tends to decrease with increasing operating temperature. This is of great importance in technology development of PSA processes for CO2 capture using CALF-20.